So let us now summarize what we've been doing in the course till now. So we basically began by speaking about the various branches of game theory. Then we delved into the non-cooperative game theory, which is the branch of game theory where the basic model allows for any strategies, not just for how coalitions are formed or something else, but any strategies. So players choose independently their strategies. That's why it's called non-cooperative. They may cooperate sometimes, but the strategies as themselves, they are by definition chosen by the separate players. And in particular, we delved into strategic form games. So we looked at the strategies without looking at the details of how they are built, like extensive games looked at. And now let us give a more detailed summary of the course. So what we are going to look at is first the areas of game theory, at least the areas we looked at. Now we delve and look at the areas of non-cooperative game theory. First, we also discuss the assumptions and the results of utility theory we use, which is important because it models what agents want. Then we are going to look at the concrete areas. So first, we look at the notion of the solution concept, the basic solution concepts which are dominant strategies and Nash equilibrium. Then we look at one of the most important classes, which is potential games, which models agents who have common goals, and an isomorphic class, but a class which is which actually may seem different because it's defined completely from a concrete perspective of congestion, several agents using the same resources. Then we are going to look at another class of games, which is in a way opposite to potential games, because potential games talk about common goals, and here players share a constant sum. So what one gains is what the other loses, and therefore it's the game where you have opposition. Those games were historically modeled by von Neumann and Morgenstern, so these are very, very important games historically as well as for the theory itself. Then we are going to talk about the existence of Nash equilibria in some games, and in particular in the mixed extensions of games, which are called mixed Nash equilibria. We call them mixed Nash equilibria. That can be one of the interpretations of mixed Nash equilibria is that players randomize. So the strategy of such a player is a distribution over the set of all the original strategies, so-called pure strategies, but that's only one possible interpretation. And till now, scientists, or even philosophers of science, or let's say game theorists and philosophers of game theory, because game theory is mathematics and social science, somehow in between. That's why I'm a bit hesitant to call it science in the English sense of the word. So anyway, till now people who work in the area are not sure about the interpretation. Of course, the mathematics is not a topic of discussion, of disagreement, I mean, but the interpretation is still now. And we're going to talk about a very interesting variation of Nash equilibria, which is called strict Nash equilibria. And then we're going to talk about dominant strategies which are always the best. It can be strictly, not strictly dominant or weakly dominant, and the result of dominating strictly dominant strategies, which at any time of this process, which is called iterated elimination of strictly dominant strategies, you remove any number, not necessarily all, but any number of the currently strictly dominated strategies. I should have written here strictly dominated strategies, not strictly dominant, strictly dominated strategies. Let me fix it. dominated. Strictly dominant, we don't of course eliminate them, but we eliminate strictly dominated strategies. So the result of dominated this process, regardless the order, the result is always the same, and it's so-called the set of rationalizable strategies, which is the set of all strategies who can be a best response to some strategy, which in turn can be a best response to some strategy, and so on. So it does not have to be really the best response to what the other players do. It has to be a best response to what they could have done if they best responded to what the others could have done, and so on, without a limit. So it's less demanding than Nash equilibrium. It includes Nash equilibria, but it's less demanding. It's what we can rationally, when we think of the players as being indefinitely rational, what we can expect them to do. And that can be shown to be exactly the result of any iterated elimination of strictly dominated strategies. On the other hand, iterated elimination of weakly dominated strategies, first of all, does not always lead to the same result. And second, it can result not in eliminating Nash equilibria, and in particular, eliminating rationalizable profiles. So it is not something we usually do, eliminating weakly dominated strategies. Then we continue with the areas of the course. So the zero-sum games, but it's depends on all games. Max-min, that is a term which was originally motivating zero-sum. That's the best a player can do, given that the other player always hits that player as much as possible. And finding that in the zero-sum case, it is equivalent to finding a Nash equilibrium, or in constant sum games in general. But in a general game, there are other ways. We also learn to find the mixed Nash equilibrium. So finding Nash equilibria, we just check all the possible equilibria in a general game. And finding mixed Nash equilibria is for that we use certain equations and certain lemmas. So then we also talked about symmetry games. So when the utility of a player depends only on the strategy constellation and not on which player does what. So if I do A and let's speak about two players, for example, my colleague does B, then I get the same as my colleague gets if she does A and I do B. So it's only important what I do and what the other person does. And this can be generalized for any finite at least number of players. And we also prove that any symmetric game has a symmetric mixed Nash equilibrium. And we also speak about efficiency in games. So efficiency is the measure how much the worst or the best, depends which measure we use, prices, finality, or stability, how the worst of the best profile can be, in how much it's worth relatively to the best possible profile if we had a benevolent dictator. And this efficiency, so it's a measure of a certain solution concept in a game. And we look at the 4 very important games and we study that. Of course, we only scratch the surface of this very important topic, which is practically important, clearly, because we want to know what is the practical bound we can guarantee, and if we can guarantee, that's good. If we cannot guarantee any bound, then we need to regulate, maybe we need to change the game. So it's definitely practically important. It's very important because also theoretically, because it motivates researchers to understand the structure of the game, prove those bounds. It motivates the researchers to use different techniques to obtain those bounds. So that's definitely a very practical and theoretically important topic. And in general, various games are studied till this day. Then we are going to study several generalizations of Nash equilibria. One is the Nash equilibria when randomization can be correlated, unlike a mixed Nash equilibria when everyone randomizes independently of the others. Correlated equilibria assume they have a common source of randomization, and that allows them, like people who arrive at an intersection, they can look at let's say traffic lights and decide what they do. So that's a practical and of course theoretically important area. It also helps computing. It's much easier to compute than mixed or pure Nash equilibria in general, but we want to delve into that. We don't delve into that in this course. Now we also talk about another generalization along the lines of a set of players deviating, and it's called strong Nash equilibrium. That's also a very important topic, because if you can guarantee that no set of players can deviate profitably, it's a much better and a much safer situation than if you can only guarantee that nobody can deviate unilaterally in profit. And of course, it's also important, the evolutionary stable strategy which we study is a very basic notion in evolutionary game theory, which is also very important, for example, for analyzing biology and for analyzing social processes. It can be extremely important for practical applications, and also theoretically interesting and illuminating sometimes. And we are going to again scratch the surface, as this course mostly does, and study the notion of evolutionary stable strategy. So that's the overview. What we have done actually, what we are going to review in a little bit more detail today. So first, now let us simply review those topics I've gone over in a more detailed manner. And that's so what I've just done till now, 1 and 2, is the summary of today's lecture, which is a summary of what we've done till now. So what is game theory? Game theory is the mathematical analysis of interaction. Now we model a part of reality, then given the model, we use that to predict what will happen using mathematical tools. So the model, of course, should be built with using some psychological, sociological, economical, and so on knowledge. So prediction of what will happen, it requires a definition what we mean by a solution of such a game. So there are solution concepts which say, okay, I consider this and this and this to be a solution of a given model. So a model can be a strategic form game, and the solution can be Nash equilibria, for example. And then that would be, according to that model and to that solution definition, that would be a prediction of what happens. Now, game theory, which is what I've just described, is dually complemented by mechanism design. And there, the model of reality is a kind of equipped by a mechanism of how actually, what are the rules of the game, let's say, what are the exact rules of the auction or of the election and so on, and what are the laws in the society, for example. And that mechanism, we need to select a mechanism such that the participants, for example, rational people, let's say, will be motivated to behave as we want them to behave. So unlike game theory, which models reality, given the model, the reality, it predicts what will happen. Here we have some behavior which we want to have, and we need to arrive at the behavior, we need to motivate that behavior by constructing the reality appropriately. So we don't go from reality to the behavior, but we rather go from behavior to what we want, to what we need in order to motivate the behavior. Yes, so we study game theory in this course, and game theory models include non-cooperative and cooperative game theory. So Cooperative means that the basic actions are coalitions, and non-cooperative means that the basic actions can be any strategy, and so the strategies are, at least per se, they are independent. Of course, it can be that what I do, what I get eventually from a strategy profile depends a lot on what others do, but the strategy of me, by definition, the strategies of mine are by definition freely chosen by me. I can freely choose anything I want, even if that's not something I would like, even if that's eventually won't influence me as I want. But the definition allows me to choose some strategies. So that's the source for the word non-cooperative. They may cooperate, but the idea that they choose freely, and this can be such games which we study actually can be either static or dynamic. Now we have been studying static games when we just look at some strategies, and that's what happens. A dynamic game looks at the steps from which a strategy is composed, which comprise the strategy. And so these are, for example, called extensive games. So they model the extension of play. So when I know of what happened till now, how I can use this knowledge to choose what is going on, what I may remember, and so on and so forth. It can also explicitly model randomness. So not that I randomize my strategy, which is something we can do in this mixed extension, for example, or correlated equilibrium, but that there is independently an action by nature. We can only enter this randomness in the static games. We can, let's say, enter the expectation to the utility function, but the extensive games, dynamic games, allow modeling this implicitly. And also, by allowing to model information, we can model perfect information, when I know what has every player knows what has happened till any action of that player, and imperfect information, when I know that I am in one of a set of states, which is called in the information set, and I don't exactly know in which state I am. For example, if I want to model a match in pennies, I don't exactly know which one you chose, 0 or 1, when I get to choose it. If I want to model it as an extensive game, I can use this imperfect information to model such a case. Okay, so we have been doing static, non-cooperative games, and we also discussed several succinct representation of games, a graphical game which represents players as nodes, and the utility of play can only depend on the nodes who neighbor that player in the graph. So it's a particular case which basically depicts exactly who depends on whom. And polymatrix game, that's a game where the utility of any player can be expressed as the sum of the utility from the interaction between that player and everyone else. So there is a matrix for every interaction between two players, and the polymatrix, the set of matrices for any couple, describes what the couple gains from the interaction, and that's the assumption. So not every game can be decomposed to couples, to interacting couples, but if yes, then it can be modeled as a polymatrix game. Okay, so we have been doing that, static, or in other words, normal form or strategic form games, and that's also called strategic form games. Having modeled, we look what are the solution concepts we want to use, and the solution concepts include Nash equilibrium, which can be generalized when we want to randomize mixed. when we want to allow randomizations to be correlated, it's a correlated equilibrium, or if you want to check that it's a deviation proof for sets, we speak about strong equilibrium and so on. So these are all based on the idea of Nash equilibrium. Also we discussed, for example, rationalizable profiles, which, as I said, don't assume that you need to know what the others do, and that's the appeal because it's much more practical. But you only entertain or may harbor only those beliefs about the others which can be rationalizably expected by their beliefs about someone else and so on. So it has to be a rationalizable belief. It's not necessarily a true belief. So there are, of course, infinitely many possible solution concepts. Some of those we have studied are those. And then we look at different kinds of games. So sometimes for certain kinds of games we have interesting properties. So of course most prominent are zero-sum games, potential games. We mostly look at finite games, but not always. We assume always, I remind you, that the set of players is finite, but the set of strategies did not have to be finite. So when it's finite, we call the game finite, otherwise it's a non-finite game. Then we can look at games which are repeated or one-shot. We'll only look at one-shot games. A repeated game is when you have a basic game which is repeated several times, and that defines the utilities in those basic games, and then we need to somehow define the utility of the player in such a sequence of several basic games which can be finite or not. That's usually studied as a particular case of an extensive game. We have not done that, but theoretically that can be done. So we have been doing one-shot games, and we also look at games which are symmetric. So when every player's utility depends only on the constellation of strategies and not exactly on who does what. Or a game can be asymmetric. So sometimes you can see that this sign simply changes depending on the parity of the permutation. But we didn't speak about that. And a game can be neither, of course. So there is no symmetry or asymmetry. And because there are many applications of game theory, most notably probably wars, spreading resources, modeling evolution, games in parliament, like, for example, I have the strategy to say this, and that, and we also can speak about who knows what, and model this as an extensive game, or voting, where the players can be, for example, the candidate, and then the choice of their advertised position, political statements are the strategies. That can be an example of voting games, and in general this is a very prominent, practical, important. Sometimes it predicts practice, sometimes it does not. Definitely theoretically compelling area, voting theory, which we have not been doing besides several examples. Okay, so before we delve into our topics, let me also shortly remind what we did in utility theory, which is the basis of game theory. So we assume that first of all, that's about what players gain, and we assume complete information that everyone knows the rules of the game, of the description of the game, who are the players, what each player can do, what are the utilities of each player. That's common knowledge. So everyone knows that, everyone knows that, everyone knows that, and so on. Don't confuse this with perfect information. Perfect information is something about extensive game when at the point I act, I know exactly what's been going on. That's not necessarily the case, and we have not been doing those games yet. Not deeply, at least. We've only introduced them. But the notion of complete information is something we are going to assume, unless said otherwise. That's simply everyone knows the rules of the game, everyone knows that everyone knows the rules of the game, and so on. That's called that it's the rules of the game are common knowledge. So we assume that unless said otherwise. We also assume that players are infinitely rational. So they want to maximize their utility, and they are infinitely clever unless said otherwise. And finally, we always assume the von Neumann-Morgenstern axioms, which are called linear utility axioms, which they proved in their famous theorem to be equivalent to the existence of a representation of the preference. So basic model speaks about players preferring one outcome, one strategy profile, realized to another outcome. And that preference is denoted by those curly less than or equal signs. But we are going to use mostly throughout the course. We used throughout the course. My apologies. It's not the first lecture. So we use throughout the course the assumption that we have a function which value, numerical value, expresses how much a player wants a certain outcome. And that is given by the theorem, which says that assuming those assumptions that they have, which are very logical, so not necessarily always true, but we assume them, that is equivalent to the existence of a function from the set of outcomes to real numbers, such that the outcome Li realized with probabilities Pi is not as good for the player, I think, in question, as outcomes Li realized with probability Qi, respectively, if and only if we look at just the convex combination of the utility functions values at the outcome combined with Pi's is at most, as a number, the value of U of Li's combined with Qi's. So we can represent the preference of each player with her utility. Here it's some utility and some player, assuming those von Neumann-Morgenstern axioms, which you do assume. So we can always assume that we have such a function. Okay. So let us go into the things we did. Okay. So first we spoke about basic solution concepts, dominant strategies, strategy profiles, and Nash equilibria. So a strategy, a pure strategy or a mixed strategy can dominate another pure strategy if it's always at least as good. So there are two ways of domination: being either always better or at least as good and at least sometimes better, strictly better. The first of the being always better is called strictly dominated. Being at least as good and sometimes strictly better is called weakly dominated. And there is another notion which we don't use here. We mentioned it briefly though. Is very weakly dominated. That's when some strategy is at least as good, and we don't even don't require that it's sometimes strictly better. It's called very weakly dominated. But let us just concentrate on strictly dominated and weakly dominated. Actually, we are going to mostly use strictly dominated. Strictly, of course, implies weakly, which implies very weakly. Now, a strategy is called dominant if it dominates strictly or weakly, respectively, every other pure strategy, and it's called dominated strictly or weakly if it, respectively strictly or weakly, is dominated by some pure or mixed strategy. So we can be dominated by some mixed strategy. It's enough that there is a mixed strategy, so you sometimes see, sometimes that it's always better what we do in order to, as we shall see, in order to disregard the strategy in the sense of, let's say, Nash equilibrium. It's going to be always possible. So first of all, we define as weakly dominant strategy equilibrium. That's the profile of weakly dominant strategy. So every strategy is weakly dominant. That's reasonable to assume. So we are going to work and to love most in the strictly dominant strategy equilibrium, which is extremely rare to have. Sometimes we do have it. If you do have it, that's definitely what we expect to have. It's always unique if you have it, by the definition of strict domination. And an example is prisoner's dilemma. That's a very important solution, so strictly dominant strategy equilibrium. And then we define probably the most famous solution concept in non-cooperative games, Nash equilibrium, which is a profile where no player can strictly improve her utility by a unilateral deviation. So whatever other strategy I use, I will never strictly improve what I have. I will have the same utility or worse. And strictly dominant strategy equilibrium is always a Nash equilibrium. Well, actually, a weakly dominant strategy is also always a Nash equilibrium. By definition of strict or weak domination, everyone is a best response. Therefore, if it's strictly or weakly dominant strategy equilibrium, it is a Nash equilibrium. Now, iterated elimination, however, we only work with it on strictly dominant strategy, because if we iteratively eliminate weakly dominant strategies, we can sometimes lose Nash equilibrium. We will never add one, but we can sometimes lose them. On the other hand, iteratively eliminating strictly dominant strategies never results in a change in the set of Nash equilibria. And moreover, the resulting set of this iterative elimination does not depend on the order, unlike in the iterative elimination of weakly dominant strategies, which can depend on the order in which we eliminate those strategies. When we iteratively eliminate strictly dominant strategies, the order does not matter. It will always result in the same set, and the set will have exactly the same set of Nash equilibria. So that's a nice way to prepare the game to find the set of Nash equilibria. When we look for that, to iteratively eliminate all the strictly dominant strategies. Also, the set of mixed Nash equilibria will remain the same. So you can always work well. If you have a strictly dominant strategy in the original game, then it's also strictly dominated in the mixed extension. So that immediately says that the iterated elimination will not change the set of mixed Nash equilibria. So now let us talk about efficiency of solution concept, in particular of those solution concepts which are dominant strategies, Nash equilibria and Nash equilibria. And the efficiency measure measures how the requirement that we use the solution concept can decrease the efficiency, the social welfare, relatively to the best possible social welfare which it could have been. So we use two efficiency measures. One is the most famous, I think, which is called the price of anarchy. And the other one is also famous, but less, which is called the price of stability. So the price of anarchy is, here we define it for for Nash equilibria, but we can use any solution concept which is not empty, which has at least some solution for that game. So the definition is that the price of anarchy is the worst ratio between the social welfares. So we look at the maximum possible social welfare ever, and we look at the minimum social welfare in an equilibrium. So what is the largest price we can pay for players choosing what they want, for players in a way being in the state of anarchy, because they can play anything which is in equilibrium. That's our assumption. Now we have a bit of a more optimistic approach, but still we assume that they play in equilibrium. But now we say, what is the necessary price to pay for being stable? What is formally the ratio between the maximum possible social welfare and the best possible Nash equilibrium, and social welfare in Nash equilibrium. And here, please pay attention, we can take for social welfare anything we want. We usually take the sum of the utilities, the total utility, but it can be also the minimum utility, and then we want just to make sure that the worst off player is okay. That's kind of a very socialism oriented approach, which is called the egalitarian utility. And the utility which takes the sum is called utilitarian. We just want to improve the total thing. So there are several approaches, and the eventual result depends on the social welfare definition, on the exact measure of efficiency, and of course on the solution concept in question. Usually the solution concept will be the Nash equilibrium, the social welfare will be the sum of the utilities, and the definition will be price of anarchy or stability. Price of anarchy gives a good guarantee that in the worst case, as long as you assume the solution concept, you will never lose a ratio higher than the price of anarchy. But when we cannot guarantee a good price of anarchy, it makes sense to say, okay, but is there at least one good solution? If there is at least one good solution, then we know just that we need somehow to try to coordinate players to play that. If there is no good solution, then we need to think, okay, we can only change the game. That's already a question of mechanism design. On the other hand, if all the solutions are good, so if the price of anarchy is guaranteed to be low, then we don't need to do anything. And sometimes it's really nice to know that, because if you prove that in some cases, say in some network, some game has very low price of anarchy, preferably 1, then you know that you don't need to do anything, and there is no need to employ a costly coercion mechanism, which can be not only practically costly, but also sometimes either impossible or simply morally repugnant, or something you don't want to do. If you don't want to force people to do something. The next topic is going to be, again, I should say, the potential games. That's a very broad class of games, which describes games with a common goal, played with a common goal. And there are several degrees of potential games. So we first start with generalized ordinary potential. So those are the set of games which have such potential. They are strictly included in one another. So the largest set is generalized ordinary potential. Potential is a function from the set of outcomes. So the strategy profiles 2 real numbers. And the generalized ordinary potential means that for any player, so for any profile and any player I that changes from Si to Ti, the utility change for that player, if it is positive, then that function is also positive. We don't guarantee anything else if in the other direction, if the function change is positive. We don't guarantee anything else about how large that is, but we guarantee that if the utility change is positive, for any player, because of that player's simulator deviation, then the function traces exactly this sign of the utility change. because by changing the order you can speak about the utility being negative, because it simply amounts to changing the order between the SI and TI. And anyway, so that is the definition of the generalized ordinary potential. So there is one function common to all players, which in a way traces, in the way which is exactly described here, traces the change in the changes of the all players, and that's called the potential function. So that while they have a common goal, they all want to increase the function. That can be shown to be equivalent to a finite improvement property, which is when you look at the path starting from some solution profile, you have one player at a time. That only that player changes her strategy, and then this chain of changes, this path, can consist of those changing players, or we call them deviating players, having a strict increasing in their strategy only a finite number of steps. That's called the finite improvement path property. So that those paths which consist of the unique deviator having an improvement have to be finite, and that's equivalent to having that generalized ordinal potential. And the important conclusion of having a generalized ordinal potential, which we always want to use, is that a finite game with a generalized ordinal potential has a Nash equilibrium. Because the finite game, please recall that we always assume the set of players is finite, so a finite game means that the strategy set is finite, so then the function P has a maximum, and it means that at that strategy profile where P achieves its maximum, no player can strictly increase her utility, which means that it's a Nash equilibrium. So that's the reason. So already in this weak definition of a generalized ordinal potential, we have that a finite game has a Nash equilibrium. That's a very important property. Actually, finding the Nash equilibrium in general can be hard, but we know that it exists. Now, a stricter definition of a potential game is that this implication is two-directed, so that a function is called ordinal potential, and ordinal potential if the change of utility being positive, not only does it imply the change of the respective change of the potential being positive, but also the other way around. So the change of utility is positive if and only if the change of potential is positive. So here we've been speaking about the signs and not about the exact values of the utility change and the change of potential. And that we are going to do now. A potential function, or a function, is called the weighted potential if there is a vector of real numbers such that, we call this of course the vector of weight, utility value, a vector of positive real numbers, not actually, let me see, 1 second. So if and only if there exists a vector of positive real numbers, such that the value of the change in the utility is exactly equal to the value of the change in the potential function up to this factor of the corresponding element of this vector corresponds to the corresponding weight. Since those weights are positive, so of course the sign is the same, so it implies being the generalized potential, and ordinal potential, which of course implies being the generalized ordinal potential. In particular, when the vector is ones, so when the potential function exactly traces the change into utility, then this is called a potential function. And first of all, we know that a potential function is unique up to a constant, unlike, let's say, the weighted potential, or definitely the generalized potential, or ordinal potential, or generalized ordinal potential, or weighted potential. They are not necessarily unique. The exact potential function, that is unique up to a constant. We found a kind of physical characterization. It seems similar to the characterization that every closed path has no the total change is zero, so it's a bit similar to this physical characterization. And in particular, the potential functions, starting from a generalized ordinal potential, but definitely a potential function too, when it has its maximum, as we just argued, always constitutes a Nash equilibrium. Because even for a generalized ordinal potential, its maximum means that no unilateral deviation can have a positive change in the potential, can achieve a positive state change in the potential, and therefore, even for generalized ordinal potential, in such a potential, no unilateral deviation could have strictly increased the utility of the deviator. Thereby, if there is a maximum of the function, I mean a global maximum, then it has to be a Nash equilibrium. On the other hand, it does not work the other way around. So if some player cannot locally change her utility, does not mean, even for the case of an exact potential, that there is no change, no better, no higher value of the potential somewhere else. But this can be used as a refinement of Nash equilibrium. So we can say that, okay, this is a potential game. Let us look at all the maximum, all of the maxima of the potential function. And that's known to be a subset of the Nash equilibria. So if we have many Nash equilibria, maybe we just can concentrate on the maximum of the potential function and assume that's what's going to happen. There was some experiment when it did indeed happen, that indeed was what happened. But I'm not saying it's always the case, but that's simply a possible refinement of Nash equilibria. Another important class of games is congestion games, which is unlike potential games defined in a practical manner. So we have a set of resources, and a player's strategy has to be some subset of resources. For example, the set of resources are rods, and the player has to choose a path from one point to another point on the graph. And the player pays for a piece of the rod. Let's say that the cost is the time it takes to go, and the higher the usage of that piece, the more players use that piece of the rod, the more the cost becomes, the higher, the longer it takes to pass it. So it's a model called congestion games. It's sounds like a more practical model than the model of the theoretically motivated model of potential games. But interestingly enough, they can be shown to be isomorphic. So there is a famous Rosenthal potential function for congestion games, which shows that a congestion game is always a potential game, but it also can be shown that for every potential game there is an isomorphic congestion game. So these classes are isomorphic. So the next important class is the class of zero-sum games, and since things in Prof here also hold for any constant sum game, that's also the class of constant sum games.